Series of reading paper out loud. It helps me edit papers before camera readies and hopefully makes the paper more accessible to who can't or don't want to read a paper version of the paper. I'm trying a new format I have the paper copy in front of me, but I'll also be reading from a teleprompter. So we'll see how that works. Let me know what you think. Okay, so let's go ahead and begin. I'm reading our NACL 2021 paper, Fool Me Twice, Entailment from Wikipedia Gamification. This was work that I did while on sabbatical at Google with some lovely people there. First and foremost among them, Julian. So, let's begin. Section 1, Introducing a Game of Challenging Claims. Given a statement and a large collection of textual knowledge, how do you find evidence that shows a reader that the statement is true or false? This problem takes on multiple forms in the natural language processing community. Given only a single statement and a single sentence, this decision process is referred to as recognizing textual entailment, or natural language inference. Given a single document and a vast pool of possible evidence, for example, Wikipedia, this problem is called Wikification. Thorne et al. 2018. Let's look at Figure 1, an overview of the data generation pipeline. In stages 1 to 4, players write challenging claims either entailed or refuted by evidence from Wikipedia. They are then tasked to spot the refuted claim among a group. We release the claims and gold evidence selected by the author. And you can download this from our GitHub repo, both the source code for the interface and the data themselves that we collected in Phase 1. We review existing resources for the latter task in Section 2, and how they have spawned a vibrant subcommunity around related tasks. However, these datasets fail to challenge modern NLP models such as BERT or T5 that achieve superhuman performance, despite also exhibiting annotation artifacts that hurt their generalization potential. Our goal is twofold: to build a new challenging dataset that tests models' ability to retrieve evidence and verify claims, and to show that engineering the incentive structure of data collection experiments can produce better results and make it easier for future researchers. This dataset lends itself to automatic training, and it characterizes what factual errors humans can most easily detect and which are most likely to fool them. This is analogous to the creation of unsupported or refuted claims in the wild, which are not random, but evolve as part of an information arms race. Unlike previous datasets that rely on crowdsourcing, we develop an online game to create a platform where motivated authors can create plausible-sounding facts that other users must debunk. Not only does this create more realistic claims, the best must withstand human scrutiny, it also creates a way to better evaluate the evidence that support or refute claims. As we surface the evidence, humans use that evidence to decide which claims are true or false. These signals can further improve our system. We apply baseline models for retrieval and classification to our dataset and examine how their ability to detect wrong statements differs from human. Let's take a look at Table 1, Statistics of the Fool Me Twice dataset. Each split is based on a disjoint set of Wikipedia pages. The number of tokens is an average value computed with a whitespace tokenizer. Our dataset is balanced between entailed, true, and not entailed claims. Section 2, Related Work. Entailment is a key task in natural language understanding. Dagan et al. Describe it as an AI-complete task. Solve it, and you can solve all of artificial intelligence. Typically, entailment is presented as, given a premise, Brooklyn is the most populous of New York City's boroughs, decide whether a hypothesis, Manhattan has more residents than Brooklyn, is entailed, supported by the premise. Even simple examples show the promise and complexity of this task. To recognize that this hypothesis is contradicted, a model must know that Manhattan is a borough of New York, recognize that X is the most populous borough entails X has more residents than any other borough, and correctly combine this knowledge to recognize the contradiction. Section 2.1, Entailment and Retrieval Datasets. Despite the promise of entailment, it has not been a silver bullet for the NLP community to solve artificial intelligence. One possible explanation for why is a line of work that shows existing entailment datasets have artifacts. Polyak et al. Show entailment can often be solved by looking only at the hypothesis, while Fung et al. Show that artifacts can infect the premise as well. This is especially common in the biggest datasets for NLI, such as SNLI and MNLI. While there are algorithmic solutions to addressing these issues, many have turned to building better datasets. Both Bowman et al. And Vanni et al. Propose alternative methods for collecting entailment pairs from crowd workers and measure success via improvements in other general tasks via transfer learning. While the proposed methods prove to be ineffective for that goal, we view NLI as an important end task in itself, e.g. for misinformation, question answering, dialogue, generation evaluation. Hence, we argue that constructing challenging entailment datasets is useful beyond just transfer learning. Like this paper, Ni et al. Focus on adversarial entailment, but authors only see a single piece of evidence. We expand this human-in-the-loop adversarial setting to include the essential retrieval component of fact verification. Thus, authors have more strategies on hand. In addition to creating challenging examples through paraphrasing, they can make it difficult to find relevant information in the first place or distract with related but distinct information. This is exactly the setting of a recent shared task, Fever, fact extraction and verification, which creates a more general entailment setting. Given a claim, find relevant evidence from Wikipedia, and determine whether the evidence has enough information to either support or refute the claim. This generalizes the entailment problem to a large, broadly accepted set of premises, all sentences in Wikipedia, and adds an additional retrieval step to find relevant evidence. Let's take a look at Table 2. Examples from Fever, which separates entailment examples into 3 categories. The crowd workers who authored the examples often edit the first line of the Wikipedia article, but not in ways that sound like a plausible hypothesis. We develop a game to build more complex, challenging examples. Fever has obvious connections to problems in education, journalism, and information science. Thus, it has caught the attention of a subcommunity building systems for Fever shared tasks. Despite this excitement, Schuster et al. Show that Fever has many of the same issues as entailment datasets. Fever has broad or nonsensical claims, and many of the claims are generated from the very first line of source Wikipedia documents. This is not just an artifact of crowdsourcing. A more fundamental problem is that there is not a clear definition of what makes a good Fever example. To date, adversarial Fever examples have used automatic rules to increase their difficulty. To address these identified weaknesses, Sections 3.1 and 3.2 define a game with human players whose creative winners create challenging entailment examples. Section 2.2, Gamification for data collection. Creating datasets through a fun interaction design is often called gamification. Epiriotis and Gavrilovich, sorry if I mispronounced that, focus on multiple choice question answering in technical domains such as medicine and rely on redundancy and calibration questions to generate new knowledge. The ESP game asks users to write labels for an image, trying to agree as much as possible with other players' labels. Another well-known example is protein folding, an online game that tasks players to twist and bend protein structures, often besting computer algorithms and driving biological innovations. Crucially, these games are either individual or cooperative. In contrast, Fool Me Twice exploits the adversarial nature of players fooling each other. Fool Me Twice most closely resembles Balderdash, a board game to determine which definition of a word is correct, which has been used in information literacy courses. In all cases, the intrinsic motivation driven by these games can lead to better outcomes and fewer attempts to game the system. Thus, our approach constitutes a viable alternative to traditional crowdsourcing such as Amazon Mechanical Turk, where tying payments to completing tasks sometimes hurts final results. This section outlines 2 phases. Its final form, this is a reflection of an iterative process. We first began with a paper version of the game, which showed that a time constraint made the game feel more fun and encouraged people not to read individual pieces of evidence too intently. Without the timer, people tried to look for tiny clues in the text that probably were not there. Read individual pieces of evidence too intently. Without the timer, people tried to look for tiny clues in the text that probably were not there. We then moved on to a version of the game presented via slides. The slides version of the game revealed 3 things. Only having 2 claims was enough to make the game interesting. We initially had in claims, but only one was false. People prefer writing false claims, and voters prefer choosing which evidence they saw rather than seeing evidence for all claims or random claims. Our goal is to create a computer game that produces human-authored, interesting, challenging claims paired with evidence that either supports or refutes each claim. One prerequisite for this is that claims avoid high lexical overlap with the knowledge corpus. We thus need to encourage authors to craft claims that cannot be trivially matched to evidence. While this approach has been used for question answering, which has a similar retrieval step, to our knowledge it has not been applied to entailment or fever. We recruit players from Google, all proficient in English, to playtest the game. At the beginning of each round, we ask each user to generate a true or false statement. We randomly choose a Wikipedia page as a knowledge source and ask them to highlight 1 or 2 evidence bands that support or refute their claim. They are instructed to write statements that would likely fool other players trying to determine the claim's veracity quickly and or without looking at the evidence claims that support the claim. The reward system defined in the next section is built to be aligned with that objective. To help authors write hard claims, not entirely similar to the evidence, we show the user what evidence a TF-IDF retrieval system would select from the source. We highlight the words that help IR systems select evidence. We include screenshots of the user interface and more details about our design choices in the appendix. This helps guide the user to avoid phrases that make the game too easy for players in the next phase. Because the players see evidence selected by our retrieval systems, difficult questions for players are also claims that are challenging for computers. See Table 3 for a comparison on a highly predictive bigrams between fever and fool me twice. Refer to the appendix for a detailed description of the method. Let's take a look at Table 3. Top 6 bigrams with the highest LMI for refutes in each dataset and each split. Overlapping bigrams are bolded. Compared to fever, fool me twice contains fewer bigrams that give away the label on both the train and dead set. Section 3.2, Spotting the Incorrect Statement. In the game's second phase, players select the incorrect statement from claims written by other players. To separate these 2 phases of the game, we refer to players in this phase of the game as voters. If a voter can correctly answer quickly, for example through their own world knowledge or artifacts, they get up to 120 points, the maximum possible. Claims that are so easy to identify as true or false are not, however, our goal. If the average player can tell through artifacts or common sense that a claim will not be supported, it is uninteresting as an entailment example. For example, if someone sees the claim, Tipper Gore was born in 1048, and remembers that Al Gore was the Vice President of the United States in the 20th century, they can identify that this claim is false. The author and voter split the points. Any points the voter leaves on the table go to the author. Challenging claims reward the author with more points, but easy ones let the voter increase their total. We want claims that require the voters to carefully read evidence from Wikipedia. Voters can ask for hints provided by our evidence selection system. For each piece of evidence shown, the number of points available to the voters decreases, and points decrease as time progresses as well. All possible outcomes provide useful information, correct and incorrect choices with and without evidence. As mentioned before, if voters spot the wrong statement unaided, the claim had underlying issues. When a voter can spot the wrong claim with the help of a particular piece of evidence, then this is a clue that the evidence, and the mechanism that selected it, was useful. This allows us to specifically optimize for evidence that helps players better answer questions. When voters go from confused to confident about the correct answer, that is a signal that the evidence was effective. When voters select an incorrect answer, that is a signal that the evidence was not effective, or indeed misleading. When voters need more time and evidence, and are almost fooled, i.e. think that a true statement is incorrect, this is a sign that the statement is challenging for the human-computer team seeking to verify entailment. The statement must be convincingly written, consistent with the voter's world knowledge, and also consistent with any evidence players see. Our game setting helps create conditions where these tricky examples can be crafted. We use 2 heuristics to ensure difficult claims. First, we search for examples that were consistently solved without inspecting the evidence, but were not able to find any. Next, we compute a maximum a posteriori estimate of the Bernoulli distribution of correct and incorrect votes for each claim. 5 pseudo-counts, 1 wrong, 4 correct, for each question. We use this smooth estimate rather than the maximum likelihood estimate to account for claims that lack votes. The expected value of this posterior given a beta 4,1 prior is, from Aloud et al., 2012, alpha given the counts is distributed according to a beta distribution with parameter 4 plus the sum over all counts, comma, 1 plus 1 minus the sum over all counts for the sum over I, which is over the votes, and Ci is 1 if the vote was correct and 0 otherwise. We analyze all 25 claims below a 0.5 threshold and remove 3 wrong examples. Section 3.2.1, Incentive Structure. Players earn points in 2 ways, either spotting incorrect claims by voting as early as possible, or by authoring challenging claims. They alternate between the 2 roles in every game session. These 2 rewards are in opposition to each other. Because the goal of the voters is to find the claim that is incorrect, claim authors, either entailed or refuted, only get points when voters are not fooled, but only do so after looking at some of the evidence. The total points are distributed between the voter and the authors when the voter correctly guesses, making this a zero-sum game. As a voter requests more evidence or takes more time, a larger fraction of the total points will go to the authors. Thus, authors are encouraged to write claims that are difficult. Voters are encouraged to select claims correctly. When a voter guesses incorrectly, they get no points to ensure the examples are valid. While incorrect guesses can happen for impossible claims, writing claims that are merely difficult is a better strategy, since easy claims that may be spotted quickly are awarded no. In addition to humans voting on claims, we also ask users which of the 2 claims they like more, independent of voters' accuracy. People like true claims, probability 0.39, more than false claims, probability 0.35, t-statistic 2.53, except for claims about science and technology where people prefer false claims more than true claims. Authors get points when voters like their claims. This additional incentive encourages authors to create interesting and surprising examples. Methods. Section 4, Subtasks and Models. Each of the instances in Fool Me Twice is a tuple of C, E, L. A natural language claim C, evidence E from a knowledge corpus K, in our case Wikipedia, and a binary label L. Is it entailed, or is it a contradiction? From this we define 2 subtasks following Thorne et al. The first subtask, Retrieval, requires systems to select candidate evidence from clay, including perhaps the gold evidence E. The second subtask is Entailment, where systems given claim C and the gold evidence E need to make a final prediction for the label L. We also consider an end-to-end setting where instead of the gold evidence, systems only have access to the retrieved evidence E hat at test time. In the rest of this section, we define baseline models for each of the subtasks. Section 4.1, Retrieval. Our setting is similar to the current retrieval setting proposed in the KILT benchmark, but the results are evaluated at the evidence level as opposed to the page level to represent a more realistic use case. The evidence corpus can be found online and consists of 22 million text passages, each having a length of 100 words, from 5 million pages of the English Wikipedia image from August 1st, 2019. We align the gold Fool Me Twice evidence to this knowledge source by selecting the passage with the highest overlap with each evidence sentence, according to the modified n-gram precision component of Aloud. We remove 1,598 examples where the precision was less than 0.5. We evaluate 2 baselines. The first one follows Chen et al. And uses a TF-IDF retrieval model with unigrams and bigrams and a 2 to the 20th hash bucket. The title of the page is added to the passage content for additional context. The second baseline uses dense passage retrieval using the same fixed pre-trained passage embeddings in query encoder as in Petroni et al. Section 4.2, Entailment. For the second component of the task, we follow state-of-the-art entailment models in implementing entailment contradiction binary classifiers conditioned on the concatenated gold evidence and claim using a BERT-based model. For end-to-end label accuracy, we use the same models but test only retrieved, rather than gold, passages. During training, we include both the gold and the top 2 retrieved passages. Section 5, Machines Spotting False Claims. This section shows how well existing automatic methods for entailment can detect false claims in Fool Me Twice for both the retrieval of evidence and for entailment once the results are retrieved. Retrieving evidence for Fool Me Twice is considerably harder. We also include comparable results on Fever. The documents retrieved by DPR are considerably better than the ones by a TF-IDF system for both the datasets we tested, which is consistent with other work on dense text retrieval. Let's take a look at Table 4. Claims and evidence shown to players in the voting phase. The voter must detect which claim is incorrect. Initially, the player sees only the claim. If the player can answer with that, they get the most points. Automatically found evidence is shown one by one upon request, with decreasing time waiting. If voters need more evidence or more time, there are less points available if they get the claim correct. Eventually, if time does not run out, the gold evidence selected by the author of the claim is shown. And the answer to this claim is the claim about Elizabeth II is false. Let's now take a look at Table 5. Results of evidence retrieval baselines on Fool Me Twice and Fever. R precision is the precision at K, with K the number of gold evidence snippets for the claim. Fool Me Twice is harder for both retrieval models. Section 5.2, Entailment Results. This section presents the results of training BERT baselines for the entailment task of Fool Me Twice. That is, given a claim and gold evidence, does the evidence support or refute the claim? To compare with Fever, we discard all not enough evidence examples because the lack of evidence for this class makes it trivial to classify correctly. Following Guru Rangan et al., apologies if I said that incorrectly, we first train a claim-only classifier which ignores the evidence text. Fool Me Twice examples are harder to classify without looking at the evidence, indicating that the claims contain fewer giveaway artifacts compared to Fever, as already suggested by Table 3. We provide additional discussion in Appendix C. Like the techniques proposed by Clark et al., the claim-only classifier can also be used on both Fool Me Twice and Fever to split the dev sets into easy and hard partitions. The easy partition contains all examples correctly classified by a claim-only classifier, and the hard partition has everything else. The similar accuracy of the Fool Me Twice and dev and hard Fever dev sets further suggests that Fool Me Twice is comparable to the harder and higher quality subset. We also train an end-to-end verification model that, rather than taking evidence as a given, must use noisy passages from a retrieval system. At train time, we generate multiple training instances for each claim using either the gold evidence or the top 2 retrieved examples. At prediction time, we average the logit scores of each of the top K retrieved passages. We include a so-called oracle setting for a fair comparison of the improvement margin. This number differs from Table 6 in that it uses a single gold 100-word passage as evidence, instead of short sentences, which might introduce noise. Let's take a look at Table 6. Comparison of dev accuracy between Fever and Fool Me Twice for different partitions of the data when using only claims. The partition into easy and hard splits is based on the claim-only classifier. The claim-only classifier can solve easy examples. Fool Me Twice examples are thus comparable to hard Fever examples. Let's take a look at Table 7. End-to-end label accuracy results of retrieval followed by entailment on Fool Me Twice. We vary the number of retrieved examples at prediction time. We compare against using the gold evidence as an oracle, which differs from Table 5 in using a single 100-word passage as evidence. Section 6. Human spotting and writing false claims. While the previous section focuses on how well automatic methods can detect false claims, this section focuses on human ability. Voters are usually right, and we're fooled 20% of the time. This section addresses how players are fooled and how this compares to computers. To provide a better picture of the strategies players use to craft challenging claims, we manually sample 50 instances from both the development set that both models and humans got wrong. We focus on these examples because they are the most difficult and are the emphasis of our adversarial technique. 2 claims were mislabeled, and 2 more lacked a necessary evidence span. Table 8 shows examples of each of the strategies, which we discussed in more detail in this section. Temporal. Many of the most challenging claims require an inference about time, whether one event happened before another, how long an event happened, or whether an event happened during a period. While many of these are based on years, centuries, or other explicit markers of time, some authors use narrative time. For example, the page for the novel As I Lay Dying describes the plot and order. So it's difficult for either a system or a human, given sentences, without knowing where they appear in the original page, to know when Addie Bundren dies. This shows some of the limitations of our setup. Not only must voters reason across multiple pieces of evidence, this reasoning is only possible if they know the order in the underlying evidence. Other markers of time include the pilot for the first episode of The Office. Readers must realize that if the character Kelly Kapoor was introduced in the episode Diversity Day, that implies Mindy Kaling's character did not appear in the pilot. Reasoning. A related but more general strategy requires the reader to reason, mathematically applying definitions or understanding hyponymy. For example, knowing that the child of your cousin is also your second cousin, or recognizing that this mirrors the Disney Parks East Regional Division consisting of Shanghai Disney Resort, Hong Kong Disneyland, and Walt Disney Attractions Japan, implies that there are more than 2 Walt Disney resorts outside of the United States. Let's take a look at Table 8. An ontology of human strategies for creating challenging claims in our dataset, sampled from claims that challenge both humans and computers. Paraphrase. A well-known strategy to confuse entailment systems is to change words so that there are fewer exact matches. Some of these are straightforward. Titration is used when doctors test how much sugar is in a patient's liquid waste, is almost a direct paraphrase of glucose in urine may indicate diabetes in a patient. Other paraphrases are more poetic. Charles Evan Hughes shoveled off this mortal coil in Massachusetts and then was taken to New York to be submerged in soil. Paraphrasing, Hughes died in what is now the Tiffany Cottage of the Winnebago Club in Osterville, Massachusetts. He is interred at Woodlawn Cemetery in the Bronx, New York City. These paraphrases are realistic, similar to how humans might restate facts to make them more accessible or more interesting to a reader. Diversion. An interesting strategy to fool the retrieval phase of fever systems is to create claims that point to specific text, but not the text that refutes or supports the claim. For example, following his retirement from Major League Baseball, Prince Hal became a top executive of a company, retrieves information about how Newhouser got the nickname Prince Hal and his later business investments, but not his post-baseball career in banking. Controversy. A more fundamental issue with entailment systems is that even entrusted sources such as Wikipedia contain contradictory evidence. This was most prominent with interpretations of works of fiction, where there are multiple theories about the same work. A skillfully written claim can retrieve one viewpoint while using an opposing viewpoint as the gold evidence. For example, one claim strongly took the position that the end of the movie Inception was a dream. Voters saw evidence to the contrary and thought the claim was refuted. Because systems focus on the highest scoring retrieved passages, as do the human voters, this led to both humans and computers to overlook the disputed interpretations. Section 6.1. What was difficult for humans? While the previous section focuses on strategies that challenge both humans and computers, the amount of evidence a human needs is a unique metric of how difficult a claim is for humans. Although incremental evidence is recommended for question-answering systems in Boyd-Graeber and Böschinge, to the best of our knowledge this has not been applied to entailment or validation. The claims that most challenge humans typically use diversion. For example, The Quiet Man was a song by Bing Crosby about a soldier who lost his voice from a bomb in World War II, which is particularly challenging for retrieval systems. Other common strategies for the claims most challenging for humans were paraphrase, which can hide the relevant evidence and prevent retrieval, and reasoning, which often requires multiple pieces of evidence to reach a conclusion. Section 7. Limitations and conclusion. While this paper seeks to advance the ability of humans and computers to support or refute statements entailed from a static, reliable source, the goal of examining arbitrary statements remains elusive. By construction, we have focused on statements that are incorrect because of factual error. Other datasets that use human source obfuscations or deception are more nuanced and use framing or shading, which models trained on this dataset cannot detect. Our goal is to focus on clear facts that can be recognized by computers, which is already challenging enough. Further improving verification likely requires creating targeted datasets that focus on specific strategies for creating statements that are refuted by evidence. Likewise, a more complicated task likely requires more nuanced incentives and instructions for authors. However, this dataset provides a foundation to build these richer, more challenging datasets for entailment. Thank you so much for watching this video or listening to the MP3. This is an experiment. I'm going to do this for another NACL paper in a little bit. If you like what I'm doing, please let me know. Subscribe to my channel. Leave a comment. I don't know if I'll keep doing this. It's not that much more effort, but if nobody likes me reading my papers, I'll just do it quietly to myself as I used to do before. But if you do like it, let me know and I'll keep doing it. If you want to read this paper the normal way, check the description down below for a link to the paper, the data, and also the source code if you want to try to play this game online. We're also going to be putting up a link to the game so that you can play this game